In this video, we are going to address how we are going to estimate the thermodynamic properties of multi-component mixtures. When we are preparing mixtures of more than one component, the interaction between the different constituents of the mixture becomes important in determining the total net volume of the mixture and eventually total net energy of the mixture. For example, let's mix, in our imaginary experiment, 50 milliliters of water with 50 milliliters of ethanol. When we mix them, we find out that the total mixture will come to a volume which is less than the sum of the volumes that we have introduced into the mixing container. The reason that the sum of the total volume of the mixture is less than the sum of the volumes is because the molecules arrange themselves in a manner that they conserved volume because they had attractive interactions or because smaller molecules filled the void of the larger molecules. Now, the fact that the mixture has a volume that is not additive requires that we have to estimate a volume change upon mixing. The volume change upon mixing has to be quantified empirically. We need measurements in the laboratory, and we have to find out whether this volume change is going to be negative or positive. So this diagram has on the x-axis the mole fraction of methanol, and on the y-axis volume change upon mixing in the units of cubic centimeters per mole. So we start with methanol, and a diagram with methyl formate mixing with methanol has a negative volume change. In other words, the sum of the volume of the constituents is less than the ideal mixture. Ideal mixture should have had a sum of being equal to the total of the individual components. On the other hand, when we mix methyl formate with ethanol, a different behavior is observed. This time, the volume change upon mixing is positive. The mixture is going to have a larger volume than the sum of the constituents. And we have to be able to take the volume change upon mixing into account in order to be able to make estimations of multi-component mixture properties accurately. All right, so this is about volume change upon mixing. On the other side of the board, we have an example of mixing an acid and water. We have sulfuric acid, we have water, we mix sulfuric acid with water, and we know that when we mix an acid and water, always it releases energy. So we have started with a certain internal energy of this sulfuric acid, a certain internal energy of this water. We added them together, and the total energy of the mixture is less than the sum of these energies, sum of the energies released as heat. And this is quantified in a thermodynamic chart where mixture enthalpy is plotted as a function of weight percent of sulfuric acid. This diagram is generated. This is generated for 0 degrees Celsius measurement. And as we mix, the mixture enthalpy per mass, mixture intensive enthalpy is less than the pure component enthalpies. So now we are going to develop mathematical tools to take these into consideration and estimate the properties of mixtures. Now let's put all these verbal information into a mathematical statement. So we have the mixture internal energy and this is total internal energy, extensive, is equal to number of moles of the first component that we put into this mixture times the mean molar internal energy of component 1 plus number of moles of component 2 times the mean internal energy, intensive internal energy of that pure component plus the internal energy change that occurs upon mixing. Of course, the internal energy of the mixture is N total, represented by N, times the mean internal energy of the mixture. So the sum of the internal energy of the pure components multiplied by their quantities is referred to the internal energy of the ideal mixture. The internal energy of the ideal mixture subtracted from the internal energy of the mixture is going to be the internal energy change upon mixing. In this example, it was this heat that we have released by mixing an acid and water. So now we have a new term, internal energy change upon mixing. For the moment, this is an extensive property, is equal to internal energy of the mixture minus internal energy of ideal mixture. So we have to remember internal energy change upon mixing is the difference between internal energy of the mixture, of the real mixture, minus internal energy change if the mixture were an ideal mixture. If the mixture were an ideal mixture, I could have calculated the internal energy change by simply summing up the internal energies coming to my container through the addition of the individual components. Let's just have a corresponding statement for the volume change. The volume of the mixture, let's derive the expression first of all. The volume of the mixture is equal to, if it were an ideal mixture, number of moles of the component 1, specific volume of component 1, plus number of moles of component 2 times specific volume of component 2 plus volume change upon mixing. Notice that they are all, these two are extensive and these two are intensive volumes. And of course, similarly, I can write this as N times specific volume of the mixture. Okay? And this is going to be the specific volume of ideal mixture. Okay? So, similar expression is written on the side of the board. Volume change upon mixing the volume of the mixture minus the volume of ideal mixture. And this is determined experimentally as the data shown on these diagrams. They have to be determined experimentally. But once we have them, once we have the data presented in terms of volume change upon mixing or in terms of the enthalpies of the mixture, now we can derive individual properties out of those, and we will now develop the mathematical formalism for that. Now, in order to develop the mathematical formalism, now let's look at the similarity between those two identities. I'm going to create a new parameter. I will call this theta, a molar property, a general representation of the molar property. Could be volume, could be internal energy, could be Gibbs free energy. And I will derive the expressions for a general component theta. Now, I'm going to write this expression for theta, and it is going to be valid for any intensive thermodynamic property. N times theta is going to be, now I generalize my expression. My mixture is no longer binary. My mixture is a multi-component mixture so this is pure component value. This is the number of moles that entered into the mixture plus delta theta upon mixing. Okay? This requires an empirical information of delta theta in the extensive form. We are going to do a little bit of algebra and develop expressions that are going to be hopefully more convenient and more useful. I will divide both sides by the total number of moles to have my alternative expression, and this is going to be an intensive property. Now, this additional term is going to complicate the analysis, is going to make the algebra complicated. Perhaps it is convenient to invent a new term. That new term represents the information in such a form that when we take those components and sum them up, we get the total property. That invented property will be called partial molar property. And that partial molar property is going to have the following mathematical expression. So instead of underbar, I put overbar. to indicate that it is a per mole quantity. So if I take the total property, take its derivative with respect to the number of moles of component I under the conditions that my temperature, pressure, and the other component is constant, that derivative is going to give me the partial molar property. Now let's perform the experiment for this partial molar property, all right, in our imagination and on our diagram. Let's first perform the experiment so that the concept reveals itself, and then go back and carry out the algebra. Now I'm going to take, for example, 1 mole of metal formate, all right? If this corner is the metal formate corner, and if this corner is the methanol corner, right? I have 0 methanol here, I have 0 metal formate here, so I'm mixing metal formate with metal formate here, ideal mixture. I'm mixing methanol with methanol here, ideal mixture. So I take 1 mole of metal formate, and I start adding methanol into this metal formate. 1 mole of metal formate plus 1 mole of methanol is going to bring me to 50% mixture. 1 mole of metal formate plus 2 moles of methanol is going to take me a 2/3 mixture. 1 mole of metal formate plus 3 moles of methanol is going to bring me 3/4 of a mixture. And as I keep adding methanol, I will have an infinitely dilute mixture. So I will crowd here, and then finally I have pure methanol coordinate. All right? I take 1 mole of metal formate, I keep that constant. I keep the moles of component J constant. I only change the moles of component I. In this experiment, it is methanol. So here, I'm measuring the partial molar volume of methanol in metal formate. All right? So, with this partial molar volume, I will be able to calculate the total volume as follows. How many number of moles of component I have put in this mixture? The change in the property with respect to that component in the mixture, where I keep temperature, pressure, and number of moles of everything else other than this component constant. So if I perform this experiment one by one, I can estimate the partial molar properties of all the components, and I starts from 1 and goes all the way to 2 up to all of the components. So this is the definition of partial molar property, and we are going to carry out some algebra to see how it is evolved, how it is derived. Now, let me change the color of the pen and have a signed analysis. Let us assume that this property, the total property, n times theta, is a function phi of the number of moles of the constituents. All right, so we have C components, And the mixture is a function of number of moles of constituents. Remember, we are just considering effects other than effects only related to the number of moles, keeping temperature, pressure constant. Now let's double the size to n. We have doubled the size. All right, by simply doubling the size of each of the constituents. 2n1, 2n2, 2n sub c. Between these two relationships, we see that we have a linear relationship between the function that gives us the total number of moles and the total, the function that gives us the property as a function of the individual constituents and the property. Now, if I compare these two expressions, if I multiply this by 2, all right, I get the following relationship. 2 phi, that is coming from here, is equal to phi of 2 and 1, 2 and 2, and so on and so forth. All right? This is how I get the linear relationship. This is how I conclude that the relationship is linear. Now here I established that the relationship is linear, or I can just take a multiplier outside the equation, all right, and get the same, twice as many. I'm going to do this in a different color. So I'm going to have phi of n1, n2, n sub c, and I will just make this equal to n times phi, n1 times phi. I will just take n1 out of the equation. I will divide all of the parameters, all other parameters, by n1. n1 divided by n1 is 1, n2 over n1, and c over n1. So now I have generated a relationship with respect to the relative change of the constituents with respect to one of the components, right? I have kept metal formate amount constant and changed everything else, right? So now this is my new property. My property relative to each of the constituents is equal to my property in terms of a mole number ratios multiplied by that one particular mole number. Now, we are going to call this function phi1 to differentiate from phi. Phi was a function of number of moles. Phi1 is a function of mole ratios, all right, relative to one of the components. We have chosen the first component, but we don't have to. It could be any other component. The reason that we are doing this is exactly hidden in this experiment, that we have taken 1 mole of metal formate and we added methanol onto it, so the molar ratio of metal formate to methanol or methanol to metal formate has changed while we kept the number of moles of metal formate constant. So this is total number of moles, total property, number of moles of component 1, this function phi 1, which is a function of components. All right? So we are going to take the derivative of this with respect to n1. Right? n1, because partial derivative, because we have n2, n3, n4, n sub c. And we are going to keep nj different from I constant. And also we are going to keep temperature and pressure constant. All right? So, total number of moles have n2, n3, n4, n5, but n1. So this is going to be the first term is going to be del n1 over del n11 times phi plus n times del phi over del n1 temperature, pressure, and nj different from I being constant. Right? The derivative of the first term is going to have all zeros, n1, n2, n3, and so on and so forth. They're going to be 0. Only n1 is going to be unity. So this is phi, theta, plus n, this component, and the derivative of this with respect to. This is going to be equal to the first term, again, phi 1, right, del n1 over del n1, plus n1 times, now this phi 1 is an implicit function of n1, right? So phi 1 is a function of ni over n1, right? So I have to take the derivative with respect to this, then differentiate this with respect to that. n1 times del phi 1 over del ni over n1 times del over del n1 times ni over n1. And I have to do this for all the species, right? I starting from 2, going all the way to C, y starting from 2, because I eliminated n1 from this equation, right? All right, now let's take this derivative. Let's take this derivative in a different color. Del ni over del n1. So it is, I'm going to take the derivative of a ratio. Del ni over del n1 is 0, right? Ni is different from n1. Minus del n1 over del n1 is 1 divided by 1 times ni, right? Divided by and n1 square. All right? So this term becomes phi1. This n1 square cancels with that one, plus 1 over n1 times summation of del phi1 over del ni over n1 times ni. Now I'm going to multiply both sides by n1. To be equal to that. Now I have multiplied both sides of this expression, this derivative, by n1. Now this n1 times phi1 was equal to phi. Phi was equal to n times theta. Phi was equal to n times theta. A little bit convoluted, but this is equal to n times theta. All right? And if I revert back to the original, all right, if I revert back to the original, I have d del over del n1 times n times theta without carrying out this differentiation. I moved back 2 steps. That is equal to n times theta plus minus del phi1 over del ni over n1 times ni. All right? So if I divide again both sides, or if I just take this into a parenthesis of n, I will get a mole fraction of component I, but I still have a complex relationship that I have to deal with. Now I have to work that out. Now let's review what we have done and the additional line that I have added in the meantime. Now we have started by the definition of total number of moles multiplied by the property, intensive property, is equal to the number of moles of component 1, metal formate, multiplied by this new function that we have generated. Subscript 1 refers to the fact that we have removed component 1 from this equation and we have scaled all the other components relative to this first component. All right? So everything is coming from here. We have differentiated this expression with respect to n1. This side of the expression yielded phi1 plus n1 times the differentiation of this phi1 with respect to n1, but since our function was implicit in terms of n1, we had to do a differentiation, sequential differentiation. We have found out that the derivative of ni over n1 with respect to n1 is equal to minus ni over n1 square, and we have n1 cancelling this n1 square to get this n1, and then we multiplied both sides of this equation with n1, and finally we obtained that this n1 was forgotten in the previous version, times del over del n1, n times theta is equal to n times theta minus this group of algebra. How did we arrive at here? When we multiplied both sides of this equation by n1, we obtained n1 phi 1, n1 phi 1 is equal to n phi. So now we have placed n times phi here. Now we are going to look for theta equivalent of this phi derivative. All right. So in order to find that theta equivalent of this phi derivative, we are going to start from n times theta, which is equal to n1 times phi 1, again from here, but we are going to differentiate this with respect to n sub I, any component, keeping temperature, pressure, and number of components, number of moles of components J, different from I constant, all right? And this is equal to n1 phi 1, which is a function of ni over n1, all right? So del n1 over del ni is going to be equal to 0 because we are just working on a function that doesn't have n1 as a parameter. All right, so the second term is the differentiation of this phi 1 with respect to ni. All right? So that differentiation is going to be equal to del phi 1 over del ni over del n1, because when we take this derivative, let's use a different color to take this derivative. This is going to be del nj over del ni, 0, del n1 over del ni, nj, del nj over del ni is going to be 1. This is going to be 0 divided by n1. This is only if j is equal to I, and if j is not equal to I, the differentiation is going to be 0. As a result, instead of j, now we are limiting ourselves to I. Every other component has gone to 0 except I. All right, divided by n1, and this divided by n1 cancel with this n1. So at the end, this term, del phi 1 over del nj over del n1 term reduced itself, the summation term reduced itself to this, and now we can express this in terms of del n theta over del ni under the conditions that we keep temperature, pressure, and nj different from I constant. So this is our expression. del phi 1 over del ni over n1. That's what we were looking for. Del phi 1 divided by del ni over del n1. And now we are going to take this one, substitute in here. All right. What is this equal to? This is equal to del n theta over del ni. All right. This is equal to del n times theta over del ni keeping temperature, pressure, and Nj different from I constant. Now, I think we arrived at the needed relationship. So let's clean this up and see what we have. N1, del over del N1, N times theta is equal to N times theta minus del N theta over del Ni times Ni. So let's just revert the algebra. We are going to take this to the other side of the equation. All right, and we are going to get an expression for N times theta. So here, N1, del over del N1, N times theta, plus summation, and starting from 2 to all of the components C, del n theta over del n I times, of course this is T, P, and J different from I times Ni, or Ni different from Nj, is equal to N times theta. Now if I take this one and put this in the summation sign, all right, I can start this from 1, right? It's the same. I'm taking the derivative of n theta with respect to ni, multiplying it by ni. There we go. N times theta is equal to summation n starting from 1 to C del n theta over del n I T P n I different from J times n I is my final expression, and here I have derived an expression that is going to give me the total property in terms of the relative changes of this total property with respect to addition of each and every component. And this derivative is now our partial molar property. The change in the total property with respect to a differential change in the component I, keeping everything else constant. Right? This is the partial molar property. we're going to remember this. So this is theta I is del theta over del Ni, keeping temperature, pressure, and Nj different from I constant. This is total property, and this is N times theta also. All right?